Today I will briefly go over the upcoming homework, the homework assignment 6. So for the first question, you have a pretty standardized t-test question. And remember the formula for the t-statistics is x minus mu divided by the standard error. And the standard error is given by s over square root of n, where s is your standard deviation and n is your number of observation. So basically you just have to, first you have to calculate what's your observed mean, which is your x bar. You just add all of them and divide it by n, you get your x bar, and then you're gonna calculate your standard deviation, your s, which I believe can be calculated by a solver, or if you prefer, you can use a calculator to do it. It's not pretty difficult because you only have like 25 observations, so you don't have to use a solver. And then you just need to like plug in all of the numbers, x bar minus mu divided by s over square root of n, and you get your t statistics. After that, you need to compare your t statistics with your t critical value, which can be found in your t table. You have your alpha, you have your degrees of freedom. In this case, it's 25 minus 1. You have 24 degrees of freedom, and you have alpha equals 0.1. So you can go to your table and find your t critical value and compare that with your calculated t. In this case, I believe your calculated t is much larger than the t critical value, which means you're going to reject the null hypothesis. For part B, I believe there's two ways to do it. First, you can just do exactly like what you did in part A, but you use mu equals 0.28 instead of 0.338. You just substitute 0.28 into your mu, and you like pretty much go over what you have done in part A. The second approach is through a confidence interval approach. You can calculate your 95% or 90% in this case, because I think either one should be fine. Like you should set your own alpha, be it 0.1 or 0.05, and then you can calculate your confidence interval, which equals to x bar plus or minus t critical value times the standard error. So basically you have everything. You have your x bar, which you already calculated in part A. You have your standard error, which is the denominator in your t statistics formula, and then you have your t critical value. You can do it with degrees of freedom of 24 and alpha equals 0.1 or alpha equals 0.05, because it's not specified in part B. So I think either one should be correct. And that's question 1. For question 2, here you have 33 observations, and that means you can actually do a z-score test instead of a t-test. I think somehow the cutoff is like 30 observations. So here you have more than 30 observations, so you can do the normal approximation. You don't have to use a t distribution, but you can use a normal distribution. So in the when you calculate z-score, some important thing is first like the z-score formula, the numerator is like a difference between your observation and a specific value that you're curious about, you want to testing about, right? And in the denominator, it's the standard deviation. And in this case, uh, we can very easily find the mean, right? The difference of your observation, your observed mean, and the actual mean that you want to test, right? The actual mean you want to test is 60% or 0.6, and your observation, I believe, is because you have like 24 eyes and 9 ends, right? So that means 24 out of 33 observation is good, right? There's skin improvement. So if you use 24 divided by 33, you have your observed probability of the skin improvement. And so basically that's your numerator, right? Your observation divided your observation minus 0.6, and in denominator it should be the standard deviation, and you could remember your formula from the binomial distribution, because here basically that's a binomial distribution. You have you either like skin improvement or no skin improvement. So you only have two possible outcomes with the probability summing up to 1. So, and by the way, because here you have like 33 observations, so basically your binomial distribution could be approximated to a normal distribution. So the way to find variance is through the formula NPQ, or in this case, since you want to find the variance of the probability, not the variance of the number of people, so your formula should be PQ divided by N, right? So you have your observed probability of success, and then you use 1 minus that, you get your observed probability of failure. I call it P and Q, the probability of P and Q. So your formula should be PQ divided by N. That's the variance of your probability. And in your z-score formula, what you need is a standard deviation. So you have to take the square root of what you just computed of the variance, and you get your standard deviation. So basically you have everything in your z-score formula. And then like lastly, you have to compare your calculated z-score with the z-critical value, which again can be found in the table, the z-score table. And then moving to question 3, it's a sign test. Sign test basically compares like the difference of two sets of observation, and kind of ignore the magnitude of the difference, but just care about the sign of the difference. And I kind of forget the Darwin's experiment, but if I come up with like my own example, for example, I have a hybrid rice, I have a normal rice, like the same species but different subtype, for example. So I want to study whether hybrid rice is better, namely whether hybrid rice grows higher than the normal rice, right? So to do the sign test, my approach is first I go to one location, maybe in this location I find one hybrid rice. I also find one normal rice, and I'm gonna compare which one is higher. And then I move to another location. I do the same. I move to another location. I do the same. And my null hypothesis is the two subtype of rice do not have any difference. Or in other words, the hybrid rice is just as better as the normal rice. That's my null hypothesis. And if that's correct, what I'm gonna find is basically half of the locations I go to, I find the hybrid rice grows higher, and half of the location I find the normal rice grows higher. And if that's the case, I conclude those two subtypes do not have any difference, because half of the time this one is better, half of the time that one is better, right? So intuitively, that's how the sign tests work. The problem of the sign test is apparently we do not care about the magnitude of the difference, right? Maybe there is a half-half distribution. However, the hybrid rice, so when the hybrid rice is higher than the normal rice, it's higher by like half a meter, for example. But in the case when normal rice is higher than hybrid rice, it's just higher by several centimeters, for example. So if that's the case, a rational person would conclude maybe the hybrid rice is better. But according to the sign test, the two do not have any difference, because the sign test only cares about the sign of the difference and ignoring the magnitude of the difference. So basically here, my null hypothesis is the two subtype, they are the same. And if that null hypothesis is correct, so it's equivalent as there's 50% chance of finding subtype A is better, and there's 50% chance of finding subtype B is better, right? So that's my null hypothesis. And so in all kinds of statistics tests, after setting the null hypothesis, I'm gonna find out the probability of the null hypothesis being correct. And in a standard way, if that probability is lower than 5%, I'm gonna reject the null hypothesis. And here we use the same idea, right? My null hypothesis is a 50% chance, and then I'm gonna calculate the probability. So I believe in Darwin's experiment, I have 15 sets of observations, and among them, 13 of them have a positive size. I have a positive sign. So basically, like within my 15 sets of observations, 13 of them subtype A is better than subtype B, and only 2 of them subtype B is better than subtype A. And that's a sort of problem, right? You could, from that statistics, you could already see the problem, right? Because if the null hypothesis holds, right, out of 15 observations, I should have 7 or 8 observations with positive signs, and another 7 or 8 with negative signs, because we have 50-50 chance, right? But here, our observation do not agree with the null hypothesis. But quantitatively, to calculate the probability, you're going to use the binomial distribution, right? The binomial formula. And I think you have done that before. The question becomes, because we have 50-50 chance, so analogously, I use like tossing coin example. I'm tossing 15 coins. What's the probability of getting 13 heads and 2 tails? That's essentially the probability of the null hypothesis being correct. And you have done that exercise before. you use the binomial formula, like n choose k times a half to the power of something times a half to a power of something, right? That's the formula. And that probability intuitively should be low. I think it's less than 5%. That means you can reject your null hypothesis. All right, I think that's everything on this homework.